All right. So, good evening, all of you, and welcome to this revision session. Today, hopefully, I will try to cover all 4 weeks, which is very near to impossible, but let me try. We will try to finish all the contents, all the important contents for quiz 2. Okay. And on Saturday, if we got succeeded in this, then on Saturday, we will do the mock problems. Okay. So, we'll try to spend some time on mock, and if you have any doubts in the mock, we can clear then. And if you have any other doubts also, you can clear in that particular Saturday session. Okay, so without any delay, we will begin today's session. And as this is a revision session, I'm not going to sit and discuss the theory, the proof, or we will not be spending too much time on that. Rather, we'll take up problems and we'll try to solve it. And if at all any theory required, we will just quickly revise or recall the theory and get back to the problem. Okay, so with that, let us start with the week 5. So week 5 is all about system and its properties mainly, right? So if an input and output relationship of a system is given to us, we should be able to comment on the properties of the system. Say linear or not linear, time invariant or time variant, causal or non-causal, stable or not stable, unstable, invertible or not invertible, and there is memory less also, which is sort of important property. We will do all of them. Uh, is my volume okay, or should I? Is this fine? I see is a comment
Yes, sir. Fine. Now it is
saying
fine.
fine, no?
Yes, sir.
Okay, great. Uh, yeah. So what is linear? Let us quickly. Okay, so before we start this problem, quickly we will write the properties. Okay, so what is linearity? Or when
Satisfactory
do I say
proportion.
system is linear? When I input x1 of t, one input to the system, and if I get an output, say y1 of t, and I input another input x2 of t, which is not equals to x1 of t, some other input goes to the same system and gives me y2 of t. So we say the system is linear if I send the linear combination of these two signals, which is alpha times x1 of t plus beta times x2 of t as an input to the system. My output should also be alpha times y1 of t plus beta times y2 of t. So if it is happening, then we say system is linear, right? So if not, then it is not linear. What is time invariance? So if I delay the input, my output should also be the delayed output, right? So it's a two-step process. You send an input x of t to the system. You will get some y of t. Then you delay this signal y of t, maybe by t naught units, right? Or t minus t naught or whatever. Okay, so you delay. And then what we do is we interchange the system and the delay. So we delay the input first. And when we delay the input, it will just be the shifting. Now this x of t minus t naught goes into the system. And the output, if you call it as some y of t, sorry, y prime of t, something, not y of t. You call it y prime of t. So then we say system is time invariant. In short, we write it as TIV if this y prime of t is equals to y of t minus t. So the delayed input results in the delayed output. Okay. So x of t minus t naught should also give me y of t minus t naught. All right. So that's time invariance. We'll also see the other properties, memoryless. So the memoryless property is, what is memoryless property? Output values should only depend on current input values. Yes. Any doubt?
Sir, in memoryless system, when we give input as differentiator, means differentiator is the system.
Yeah,
Then
I will discuss that.
okay.
Yeah, you finish the question. I have that in my
Sir.
mind.
Yeah, means in sir while means in that lecture, YouTube lecture, means that in that lecture,
lecture videos.
sir said that differentiator and integrator are memory systems, but in the solution given it's memoryless.
Okay.
For our assignment solutions.
Okay,
Sir,
solution PDF has
exactly.
it, I guess. Correct. I think the evaluation is correct, but the PDF has.
Yes, sir.
wrong
Evaluation is
Yes,
correct,
sir,
sir.
right?
So which one is correct is my question.
It's memory It's memory, no? I will discuss that. I will discuss that
Okay.
as an example. Okay.
Okay,
We'll discuss that. So memoryless is basically output values should only depend on current input values. So something like my y of t is some 3 times x of t. Okay, so it should only depend on x of t. Y of t should only depend on x of t, not on any advanced or delayed values of the input. Okay, so this is memoryless. This is memoryless. See, y of 0 depends on only x of 0. Y of 1 depends on x of 1. Right, so nothing else. So these are memoryless properties, memoryless systems. Whereas y of t being some x of t plus 1 plus x of t. So this is a memory system, right? So when if I want y of 0, so here if I want y of 0, y of 0 is basically x of 1 plus x of 0. So for computing y of 0, which is the current value, I need x of 1's value, which is the future value, right? So this is like I need to store x of 1 also to compute y of 0. So this is not memoryless. It's a memory. Okay, and let's say this discussed example dx of t by dt, right? So we all know dx by dt or something like this differentiator is basically the small difference in the numerator divided by small difference in time variable, right? So x of t is dependent on t. So dy by dx, right? We all would have studied what is dy by dx, the rate of change in y divided by rate of change in x. So this is basically rate, right? We would have seen this rise by run, something like this, right? So that means this dy is basically a small difference between the previous and the next term, next value. So if you look at it in that way, in order to compute this dxt by dt, we need two values of input. So the current and the previous one. So for that reason, this becomes a memory system. So this is a memory system. I hope I'm clear. Yeah, it has a slope, right? So dy by dx is a slope, no? So to calculate slope, thanks for the explanation, Nanda. So to calculate slope, no, you need 2 points to calculate the slope, right? So memoryless should only have the current value. It should not depend on any other values. Okay, so that way dx by dt is a memory. Hope this is clear. Sahita. Yes, Sahita Dev.
So it's depends on both previous value and means future value, right?
Previous value and current value. Oh, it depends
Not the
on
future
how
value.
you are taking the differentiator. There
Yeah.
are
Okay.
two types: left differentiator, right
Yeah.
differentiator.
So
Right?
now my question is that depending on that, causal also will change, right? This system is actually causal, but what if we take the left integral, like h plus x t plus h?
Correct. Correct. I
In that
agree.
case, it will be a non-causal system, right?
Non-causal system, as you mentioned it correctly. So if it is a left differentiator, that means you are taking the left point to the current point and you are computing, which makes it causal, actually.
I
Right?
mean, the other way around, it's non-causal.
Other way around, it's non-causal. If it is a right differentiator, it will not be causal.
So as convention, we take the
Convention, we take the
differentiation operator.
left differentiator.
So it's a causal.
It's a causal. Yeah. So that is why a professor would have mentioned it as causal. So if you
Thank you,
didn't
sir.
mention anything, it is said that it is taken to be a left differentiator unless it is mentioned.
Yes, sir. Thank you, sir.
Okay. Yeah. All right. So as we were discussing, what is causal? It is slight extension to memoryless. Right. So causal systems are its output values should depend only on the current or the previous input values. Right. So again, every memoryless system is a causal system. Right. So if it is memoryless system, it is causal. Right. So not every causal system is a memoryless system. That we have to be very careful. So examples like y of t being just x of t is a memoryless, implies it's a causal. So this is causal. Y of t being x of t plus x of t minus 1. This is also causal, but this is not memoryless. Whereas x of t plus x of t plus 1, this is not causal. Right? So these are non-causal systems. This is non-causal. Okay, so output values should only depend on the current or the previous values of the input. Okay, so that is causal. This is memoryless. Yeah, next is stability. Right, stability, there are many ways to check, but we follow this standard one, which is called BIBO. So if I input a bounded input to the system, I should get a bounded output. Right, so that's how we check the stability of the system. And some bounded inputs are, right, so some standard bounded inputs are some standard bounded signals. Signals are u of t. U of t is a very standard bounded signal because u of t lies between 0 to 1. If I have to be precise, either 0 or 1. And this sine, cos, these are bounded. Right, and there are unbounded also, and also DC constant. Right, so these are some standard bounded signals, and the unbounded signals are we know standard unbounded signals, delta of
Dirac
t,
delta.
Dirac delta, and R of t, which is ramp. right? And here rect t also bounded, try t. All these are bounded. Only this standard ones were Dirac delta and ramped r of t were unbounded. Okay, so
Sir,
yeah,
sir, yt equal to x squared t.
yt equals to x square t is also causal, no? Sorry, you are talking about stability, is it?
Yes, sir, stability.
Okay. So yt is equals to x square t. Is that what
Yes, sir.
you
Yes,
are
sir.
asking? Yeah, if x of t is bounded, x squaring will also be bounded, no? Is it not? So if x of t is bounded between some a and b values, that's how bounded is, right? There will be a minimum and there will be a maximum value for x of t. You square on both sides,
Yes, sir.
it will just be bounded between these two values, right? It depends upon the interval. Okay, so if a and b are positive, it is very straightforward to see. If even though a and b are negative, we can say um, it will lie between the absolute values of whichever is bigger. So it will lie like this. So min of a square comma b square x square of t less than max of a square comma b square. Okay, but still it will be bounded.
Okay, sir.
Okay, yeah. So we can use these standard bounded signals and unbounded signals to check whether the given system is stable or not. So we'll see the examples also. Okay, something like this we can check this easily. So yt being d, this differentiator dt. So if you want to check whether this system is stable or not, you input the standard signals, right? So we start with u of t. If you input u of t, which is bounded, we get y of t to be dut by dt, which is delta of t. And we all know delta of t is unbounded. So this breaks the Bibo condition, which implies this is not stable. Right? Something like this you can check. Again, there is one more standard example, which is something like x of t by t. Okay, so if you have this thing, then you just have to take your input to be, you just have to check. You start with u of t and then sine, cos, and then if you just simply take x of t to be some constant value, which is bounded. This is bounded, but if you see the output, y of t will be 2 by t, right? And this 2 by t is not bounded, it is unbounded. As t comes closer to 0, it goes to infinity, right? So this is an unbounded. Again, breaks the Bibo condition, which makes the system not stable. Okay, so this is how we check. So remember these things. So whenever we are asking about stabilities of a system, all you have to do is use these signals to try to break the conditions. Okay, so if it is not breaking, then we can be 99.99% sure that the system is stable. Okay, so what else we are missing? I think invertibility. Invertibility is, we all know. Let us do that also. Right, so what is invertibility? So if I give two different inputs, so I give one input x1 of t I get y1 of t. If I input x2 of t to the system, if I get y2 of t, okay. So for any distinct inputs x1 of t and x2 of t, if I am getting distinct y1 of t and y2 of t, such a system is called invertible system. Okay. So for any x1 of t not equals to x2 of t, if y1 of t is not equals to y2 of t, then the system is invertible. So it's like 1-to-1 mapping. So how do we break this condition? We just have to find two inputs which maps to the same output. So if we can find such an
Many
input,
to one condition.
yeah. So if we can find such an inputs, then that system will not be invertible. Right. So that is how we break the condition of invertibility. Okay. So y of t is equals to x. Y of t being x square of t. So this we can see, no? So one input x1 of t, I will just give a constant signal 2. And another input, I'll just give it as -2. Yeah, it's like horizontal line test. Very good. So which breaks the 1-to-1 condition. So for these two inputs, we'll get the same output y of t, which is 4. Again, a constant value. Right. So this breaks the condition for invertibility. And this is how you should remember. Right. So there should be a 1-to-1 mapping between the input and the output. All right. So these are the system properties. We all know that. So let's try to use them, use the conditions and try to comment on whether the system is linear, time invariant, causal, stable or not. So let us be linear, time invariant, causal, stable, invertible. Okay, so this is like practice for all of us. So what I recommend is all of you try doing this and we'll check our answers together. Okay. So let's start with the very first problem, which is like the scaling. Right. So y of t is x of t by 5. So the system is just scaling the input. Right. So what do you think? Will this be a linear system? What do you guys think?
Yeah.
So, okay. What shall we do? Okay. So x of t by 5 is our output. Right. So if I input one input to the system, this is how we check. Okay. Our output will be x1 of t by 5. Right. So that will be my output. If I input x2 of t to this system, my output will be x2 of t by 5. What happens if I input alpha times x1 of t? Nothing. Alpha is just a constant getting multiplied. It will not, constant will stay constant. All we have to do is, you just have to scale with respect to time. So this will give me alpha x1 t by 5. Similarly, if I do beta x2 of t, That will just be beta x2 of t by 5. Right? So everything together, I'm writing it together. Okay. I hope you all understand this. So our output will be beta x2 of t by 5. Right. So this is linear. Okay. So we all agreed that this is linear. Nice. Is it time invariant?
No.
Okay. So one of you said no. So any other answers? No. Good. So it is no. So scaling, remember, no. Scaling, if you are doing scaling, it is not time invariant. Okay. You scale by any amount, it will not be time invariant because you can check. So you input x of t to the system, output will be x of t by 5, which is y of t. Then you delay. So when you delay, what happens? The output will be x of t minus t naught by 5. Right? So it's basically y of t minus t naught. Whereas you input x of t to the delay operator, it will just delay your signal by t naught. Then if you input to the system, so what does system do? It just does the scaling. Right? So when you scale this signal, the result would be so scaling will only affect the time, right? So time axis t. So t becomes t by 5. That's it. So the t naught will stay as it is. Right. So these two are not equal. Therefore, the system is not time invariant. Okay, it's not. Is it causal? Causal is very easy to check, right? So if I take output does not depend on future. Is it true? Oh, most of you are saying it's causal.
No, it's no.
Okay. Who said that t is greater than 0? Right? T is like time axis, no? It starts from minus infinite to plus infinite, right? So if I have to compute, say y of minus 5. So what input value do I need? So y of minus 5 is x of minus 5 by 5, which is minus 1. Right? So with respect to t is equals to minus 5, t is equals to 1 is a future value. Right? So this is not causal. Okay, so be careful. Again, if it is scaling, then it will not be causal. Okay, any scaling involves, it will not be causal. What about stability? Will scaling impact the amplitude values? If x of t is bounded, will the scaled version be unbounded? Is there any possibility? Anybody? No. Right, so this is stable. So you give a bounded input, x of t, if x of t is bounded, any scaling version of x of t will be bounded. It is stable. Invertibility. Yes. So it is invertible, no? How do you prove the invertibility again? So you take x1 of t, okay, give it to the system. This gives x1 of t by 5. Right? And you take x2 of t, which is not equal. Then if x1 of t is not equals to x2 of t, then you scale x1 of t and you scale x2 of t. They will not be equal, no? Right? If these two are not equal, these two will also be not equal. Correct? So it is invertible. All right. So yeah, see, even scaling took us some time to understand or give comment on the properties. Okay. And if this integrals and differentiation comes into the picture, then it is going to be a little more difficult. So now let's try to solve the second one. Okay. So this is an integral operator, and the integral limits are starting from minus infinite to 2t, not t. Okay, so be very, very careful about this. Now let us comment on this linearity. So what do you guys think? Linear? Is it linear? Linear is easy, right? So alpha times. So integral has this property, no? If you have scaling and summation inside the integral, you can split the integral, and even the scaling factor goes out. Right? So it is linear. I think if you have any doubts, you ask me. Okay, I'll have to pace it up. So we are still in week 5. Okay, so this is linear. Is this time invariant? Yeah, time variant. This will not be time invariant, right? So this will be a time variant system because the reason is here. So even the integral limits are are depending on t, right? So this y of t minus t naught is basically minus infinity to 2t minus 2t naught x tau d tau. Okay. Whereas you delay the input and then send it to the system. So if you delay the input and send it to the system, the output would result in this fashion. Right. So you are just moving your input by t naught units. So therefore the integral will also move by t naught units. So instead of 2t, it will just delay by t naught units. So this will be, these both are not equal. Right. So I hope you get this sense. So if you guys have any doubt, please do ask me. Okay. So don't stay silent now and suffer in the exam. Okay. That's the difference. So delayed input doesn't provide us the delayed output. Therefore, it is not time invariant. Is this causal? Right. Just look like if I want to compute y of 1, I need the input values till x of 2 because I am going to compute the area under the curve basically. Right? Integral is computing, right? Integral is basically adding all the values, continuous summation. So if I want to compute y of 1, I'll have to integrate from minus infinity to 2 x tau d tau. So that means I need to know the function x tau, the input values till 2, which makes me to use the future values also. This is not causal. Is this stable? Is an integral operator stable? Okay. Okay. How do I break the integral operator? So which bounded input provides me an unbounded output? Surprisingly, u of t helps in, yeah, u of t helps us in many possible ways. Okay, so if you just take x tau to be u tau, right, or your input is just standard unit signal, unit step signal. Okay, then the integral of unit step will result as, what is integral?
Ramp.
Ramp. Right, so here I will write, so integral of minus infinity to 2t u tau d tau. Right, so this results in integral till t, it results in r of t. If it is 2t, it will result in r of 2t. Okay, still it is a ramp. So bounded input, but an unbounded output, which makes this system unstable. Right? Invertible. Are integral operators invertible? Anyone? Okay. One of you said it is invertible. Anybody else? No comments. Huh? Okay. Think of this, no? Let's say you took x1 of t to be 1 and x2 of t to be 2. Okay. So what do you think the result or the output be? So if these two goes into as an input, both will be mapping to infinity, no? Don't you guys see that? Like, is
Yes,
it easy
sir.
to observe? Because it's starting from minus infinity and they are constant values. Right. So from minus infinity to 2t, the area under the curve, either you take the input as 1 or 2, both the area under the curves will map to infinity, no? So in that way, this will not be invertible also. Okay. All right. Move on. Let's move on. What if y of t is this? N is equals to minus infinity to infinity x of t into delta t minus nt. Have we seen this kind of expression so far?
Direct delta train.
Hmm? Yeah. Okay, so let's quickly comment on this. Is it linear? Linear? Yes, everybody agrees to that. It will be linear. You can check it. Is it time invariant? So whenever you see added expressions apart from x of t, right? So you can blindly close your eyes and say it is time variant. Okay, so this is not time invariant. Okay, because we have this delta t minus nt. Okay, so the delayed output will impact this delta t minus nt also, whereas the delayed input will not have any effect on this. So in that way, so if you see any other expressions containing t but not x of t, then you can close your eyes, blindly tick it is time invariant. So sorry, time variant. Is this system causal? Yes, right. So the system is causal. So you see, it depends only on the current input. Right. So this is causal. Is this stable? Stable is very easy to see, no? We have an impulse getting multiplied to the signal. Right. So impulse is, even though you give bounded input, when it gets multiplied to the impulse, it will become unbounded, no? So that is also very easy to see. It is not stable. Is it invertible? Again, okay. Is it invertible? I think I should spend some time. So how does this graph look? Right. So this thing I'm trying to. I have x of t. What is y of t doing? So let's say my x of t is some input like this. Okay. So what does y of t doing? It is sampling. Right. So sampling at every t seconds, no? Right. So when n is 0, it will just be x of t delta of t, which is this. Right. And when n is 1, we'll have this. When n is 2, we'll have this. When n is 3, we'll have this. So this is just the sampling. Right. Even the left side also will have at the integer point. So is sampling invertible? No, right? Yeah, we can always have different signals. I can now create another signal which may be like this. So exactly at those points, my signal values are the same. Right. So I can come up with two signals where this at integer values, my signal values are the same. Both will result the same output. Therefore, this will not be invertible. Okay. So don't get confused. Okay. So take a minute, think about the signal, think about the relationship between the input and the output, and then it's okay to lose 30 seconds or even maybe 1 minute. But get a good understanding on the relation and then comment. Okay. I hope this is clear. Let's move on. And yeah, let's solve this one now. Even though we have discussed these many properties, among this, in week 6, we focused on two main properties, which is linear and time invariant. And we have discussed why linear time invariant systems are our interest. right? Right? So yeah, so you should really be very nice in commenting whether the given system is linear or time invariant. So we'll quickly go through this. Again, let me okay. So if we are clear, we will quickly move. So this is linear and this is time invariant. All right. So let's solve with the first one. Is it linear? Yes, no. This is linear. Is this time invariant? Yes. Yes. Yeah. Very good. So this is time invariant also. Nice. So first option is very clear. It is both linear and time invariant. So it is an LTI system. Let's come to the second one. Is it linear? Yes. Okay. Is it time invariant? Is it time invariant? Some say no, some say yeah. So observe, no. See, that is what I said. You just take a little more time. So earlier, whatever the integrals that we discussed were starting from minus infinite to t. Right now, it is starting from 0. Right. So now if I have to check this, let's say this is y of t. Now the delayed one will be 0 to t minus t naught x tau d tau. So this is the delayed output. If I delay the output, this is what I will get. If my input is delayed, and if this goes to the system, this will be 0 to t x of t minus tau minus t naught d tau. Right? Now if I take this as some other variable, a change of variables we use, let's say this is omega. If omega is tau minus t naught, right? So then when tau is 0, my omega will be minus t naught. When tau is t, my omega will be t minus t naught. Right? So there is a change of variable here, and d omega will be d tau. So now this will be equals to minus t naught, t minus t naught, x omega d omega, you can replace it back to x tau d tau. So you can clearly see, no, this is not equals to this, because the lower limit here is 0, here it is minus t naught. So that is why just be little careful, look at the expression clearly, and then you comment. Okay, hope this is clear. All right, coming to option C, is it linear? No. Yeah, because of this. So whenever you see any constant value getting added to the system, added to the relationship, straight away it will not be linear. Okay, so this is no. Time invariance. Yes. So there is no difficulty. If you delay the input, you will get the delayed output. So there will not be any difficulty. Okay. So the last one. Is it linear? Yeah, it will be linear. Right. So you take alpha x1 plus beta y x2. You will get output will also be alpha y1 plus beta y2. That is okay. Is it time invariant? Just now we discussed. It will not be time invariant because apart from x of t, I also have this cos t. Right. So this breaks the time invariance property. So that way, only option A is linear time invariant LTI system. Apart from that, rest of them are not LTI systems. Okay. So yeah, so practice more problems like this. Okay, so LTI system, at least LTI systems, and definitely given the input output relationship, you should know to comment on all the properties. Yeah.
Sir,
Hmm.
please write the equation for yt equal to cos txt for linear.
For linear,
Yeah, to prove linear.
yeah. So
Yes.
you take alpha x1 t plus beta x2 t as the input. So as the input, as this is the input, what is system doing? System is multiplying cos t to input. Right? Is that what the system doing? That is what system is doing, right? So you take the input, multiply cos t, that will be your output. Therefore, the output will be cos t multiplied with alpha x1 t plus beta x2 t. Right? And if you simplify this, alpha cos t x1 t plus beta cos t x2 t. And what is this? Cos t
Yes,
x1 t.
sir. Yes, sir.
Output of x1 t. This is output of x2 t.
X2T. Yes, sir.
So this will be alpha y1 t plus
Yes, sir.
beta y1 by 2t. So it is linear.
Okay, okay, sir.
Okay. All right. So that closes week 5. Okay. And in week 6 is all about convolution integral. Okay. So how do I do the convolution? And this convolution came into the picture because we needed the relationship between the input and output for an LTI system. So this x1t, sorry, some input x of t goes into an LTI system and we get the output. Okay. Since it is linear and time invariant, what we ask is, since I already know the system is linear and time invariant, I don't want the relationship, the input output relationship at all. All it requires is, along with this linear and time invariant, if it has the system's impulse response, I will use this linear and time invariance to compute the output for any given input. That's it. So all I want is what is the output when I input delta of t. If I input impulse as the input to this LTI, if I get some h of t, which is the impulse response, I can actually write any output in terms of input. Any doubt? Okay. No, not the frequency domain. No, this is in time domain only. We are still in time domain. So the output for any input x of t depends on only two things. One is the input and the impulse response. Right. So this y of t, I can write it as x of t convolved with, it's not product, convolved with h of t. The mathematical expression is minus infinity to infinity x tau h of t minus tau t tau, or we know the properties, right? Properties of convolution. This can also be written as h tau x of t minus tau d tau. Right. So the output of an LTI system will actually be equal to the convolution between the input and the impulse response if the system is an LTI system. Right. So in week 6, we have extensively worked on this, and that is what it is. That is what important in week 6. Okay. So given the impulse response, given the input, you should know how to compute the output. In other words, you should know how to do the convolution. Okay. Some standard convolutions are here. So if I convolve delta of t with, if I convolve delta of t with any signal x of t, or x of t convolved with delta of t, we will get back the same signal. Right? So earlier, when we took the product, that is different. Right? So earlier we saw xt multiplied with del t, it is sampling. Right? So this is different from convolution. This is actually, it samples the value at 0. So this x of t times delta of t is basically x of 0 times delta of t. Correct? So this is not equals to this. So be very careful about this. Okay. X of t convolved with delta of t will actually give back x of t. Right? Hope all of us are on the same page, right? Like, is there any confusion here? Is this okay? All right. So that is okay. Then there is when u of t convolves with u of t, it will result in the ramp. Okay, so transfer function and all comes when we discuss Fourier transforms, no? So here h of t is in time domain. So I think till week 8, we haven't pulled in frequency domain. We just entered through Fourier series, not yet reached to Fourier transforms, no? So maybe I feel it's not a good idea to bring in transfer function here. Transfer function is capital H j omega, which we are going to study maybe in week 9. All right, so let's not bring that here. So this itself is a confusing for most of us. So if I bring that transfer function, I guess we'll all be depressed before quiz 2. Okay. Hope that should not happen. All right. So let's get back. So we are still in time domain. Okay. So let's not confuse ourselves. Okay. So the next important property that is really useful for all of us is, so if I know that two signals convolve and gives me some nice signal q of t, then f of t plus some shift and g of t plus some other shifting, their convolution will be q of the summed up delays. Okay, so this is okay, that's fine. But let's not do this here. Okay, so this is one important property which we can use rigorously to simplify the convolution. Okay, so if at all question is on something like this, so if I have to solve u of t convolved with u of t minus 2. Okay, so let's do some examples real quick. So u of t convolved with u of t minus 2, what will this be? Surprising. Is it too easy or is it difficult? Okay, u of t convolved with u of t is r of t. Right, so u of t convolved with u of t minus 2. R of 2t. Okay, f of t and g of t both are u of t's here. Yeah. So you have to use this. That is why I said this property really helps us a lot. Okay, so using that property, this will just be r of t, and the first signal is not delaying. It's t, capital T1 is 0 and capital T2 is minus 2. So it will just become r of t minus 2. Right. So what about this x of t when convolved with delta of t plus 5? What will this be? Yeah, x of t plus 5. I don't know why everybody became silent here. Is it confusing or do you guys need a break? Maybe 2-3 minute break? Or is it okay? Till now you guys were little bit interactive and suddenly when convolution came everybody became silent. This convolution is that scary or? Okay, anyway, I should continue because we don't have time for quiz 2, no? Time won't stop for us. Okay, anyway, just go back to this convolution again and please practice more problems related to this. And as I said, I have also pointed this out. This property really helps us to simplify the expressions. Okay, so even if we don't know what convolution exactly is, if you know these properties, at least we can simplify the things. Okay, and as mentioned, convolution is this integral, solving this integral. Okay, so even mock has a problem related to this. During mock, we will do this even more closely. Okay, so we have problems related to this and the convolution part also. We'll do that. Okay. Okay, so yeah, so that's about convolution. So week 6 has only these things. Okay, so that is why I didn't want to stress you guys too much on week 6 contents. Week 6 is majorly you should know. Yeah, maybe you should see that well understanding MATLAB simulation, which one signal moves and the other signal stays as it is, and then you will see a nice plot of convolution coming in. Okay, so maybe I suggest you guys to do that. Okay, so majorly week 6, I wanted to point out the important concepts. So one is, given the impulse response and the input, you should know how to compute the output. So for computing the output, it is just the convolution between the input and the impulse response. Okay, so that means computing this integral, and then you should know these properties to simplify some big expressions. Maybe I will put it as an example here. Okay, so let's say you have something like this u of t minus 5 minus u of t plus 2 whole convolved with delta of t plus 5. Okay, so if it is like this, then either you can solve this u of t minus 5 minus u of t plus 2, which will give you some rect in some region, and then convolve with delta of t plus 5. But you can do it better with properties, no? So you have a distributive property, which is like u of t minus 5 convolved with the delta of t plus 5 minus u of t plus 2 convolved with delta of t plus 5. And then you use the properties. So u of t minus 5 convolved with delta of t plus 5. This will just give us u of t minus 5 plus 5. Right? So anything convolved with delta of t, I'll just get back the same signal. So it will just be unit step 1 minus u of, use the same property, 2 plus 5, which becomes 7. And this will be u of t minus u of t plus 7. Now, if I have to plot this, u of t is this, and then u of t plus 7 is advanced by 7 units. And if I subtract this with this, yeah.
Nothing, sir. Nothing. Sorry.
Yeah. Okay. So if I subtract this, subtracted signal will be this violet one. This will be 0. 0 minus 0 is 0. Then 0 minus 1 will be minus 1. So it will just go to minus 1. And then 1 minus 1 will be 0. So this violet one is our signal. Right. So that's it. All right. So convolution properties helps us to simplify.
Sir, please again tell this minus.
Which one? Okay. So the orange one is u of t plus 7. Correct?
Yes, sir.
This red one is u of t. Now what am I doing? I am subtracting this red signal. I am subtracting this orange signal from the red signal. Right?
Yes, sir.
So till this point minus 7, both the signals are 0. So 0 minus 0 will be 0. So
Yes,
even
sir.
the violet one will be 0. Between minus 7 to 0, u of t plus 7 is 1. U of t is 0.
Yes,
So
sir.
u of t is 0 minus u of t plus 1 is 1. So 0 minus 1 will be minus 1.
Yes, sir.
Right?
Okay.
So that
Yeah.
will go negative. And again from 0, right to 0, both are 1. U of t
Yes,
is 1, u of t plus 7 is also 1. So 1 minus 1 will be 0.
0. Yes, sir.
Okay. So this violet one is u of t minus u of t plus 7.
Yes, sir. Okay.
Okay.
Done.
So
Yes,
this
sir.
way, you have to use the convolution properties, majorly this distributive property and this one. Yeah, everything is important. U of t convolved with U of t also, you should know that it is R of t. And anything convolved with delta of t gives back the same signal. So these are practice more problems related to these properties usages. Okay. With that, I wanted to close week 6 here because nothing else that is majorly important for quiz 2 at least. Okay. So we'll do if at all I miss something, we'll do it on Saturday. Okay. So now let's jump to week 7. Week 7 is Fourier series, right? Any periodic signal can be written as the linear superposition of harmonic sinusoids, right? So x of t is equals to summation k is equals to minus infinity to plus infinity ak into e power j omega naught kt. So this we know, okay, this is kth harmonic sinusoid, right? So j omega naught t is the kth harmonic sinusoid. And this AKs are the Fourier coefficients. Right. So all we have to do is express the given signal as summation of this kth harmonic sinusoids with some coefficients. So it's like linear combination, right? Something like this. So we'll do this. Let's say we have this kind of expression given to us as a signal. We have to find the Fourier series expansion of x of t, right? So all I have to do is, always remember, all I have to do is to find these coefficients, right? So what are these AKs for each e power j omega naught kt? And here omega naught is the fundamental mental frequency, which is 2 pi by capital T. Again, what is capital T? Capital T is fundamental time period of the signal x of t. Correct? So j is the complex number, t is the time axis. Okay, so all we have to do is somehow convert this in terms of linear superposition of phasors, harmonic phasors. Right, so for that, what we can do, we should know how to write this sine square theta and cos square theta. So do we know any formulas for this? Did we encounter or have you guys came across these kind of formulas anytime?
Yes, sir.
Yes, sir.
Yes, no? Cos square theta also is 1 plus cos 2 theta divided by 2. Right? So this we have seen. We'll use the same thing. If you use the same thing, we'll have x of t to be 1 minus cos 2 times 2 pi t divided by 2 plus 1 plus cos 2 times 3 pi t divided by 2. Now this is like half minus half into cos 4 pi t plus half plus half cos 6 pi t. Right, so this half and a half gets added up together, which will be 1 minus half cos 4 pi t plus half cos 6 pi t. Now at least you guys should tell me what is the time period of this signal. So what is capital T? So I'll give you a minute. So you know individual time periods, right? So if I am interested in the overall time period, okay, 1. Nice. One of you said that. Let
Yes,
me
sir.
wait for others. Will it be 1?
Yes, sir. 1.
Okay, great. Good. Actually good. So I'm not solving it, but you guys can try it out. Time period will be 1. So if time period is 1, what will be the fundamental frequency? 2 pi. Right? So
Yes.
2 pi by t, which is 2 pi. Okay, great. So after that, what we have to do is 1 minus half. Now cos 4 pi t. How can I write this in terms of phasors? Again, I think this we have discussed very recently, right? So cos theta, I can write it as e power j theta plus e power minus j theta by 2. Am I correct?
Yes, sir. Correct.
And sin theta, we can write it as e power j theta minus e power minus j theta divided by 2j, right? So don't forget these formulas, okay? So these are really important. And yeah, so we'll use the same thing. So cos 4 pi t, we'll write it as, so 4 pi t is our theta now. We'll write this as e power j 4 pi t plus e power minus j 4 pi t divided by 2. That is cos 4 pi t for us. Plus half cos 6 pi t now becomes e power j 6 pi t plus e power minus j 6 pi t divided by 2. Right? So if we simplify this, we'll get 1 minus 1 by 4 e power j 2 pi into 2 into t. So by now you should guess why I wrote this 4 pi t as 2 pi into 2.
Yes, sir.
And then we'll have minus 1 by 4 into e power j 2 pi into minus 2 into t. And then we'll have plus 1 by 4 into e power j 2 pi 3t plus 1 by 4 e power j 2 pi minus 3t. Right? And this 1 also, we'll write it as 1 into e power j 2 pi 0 into t. So now, why I wrote in this way is 2 pi is our fundamental frequency. Right? So 2 pi, actually j, t, everything is same. So the only thing that is changing here is in the first term we have 0. We have 2 here. We have minus 2. We have 3 minus 3. Right? So if you just scroll up, we have omega naught separated. And that remaining term with 0, 2, minus 2, minus 3, 3 are this case. Right? So which harmonics are left? So the harmonics that are there here are 0, 2, minus 2, 3, minus 3. So their corresponding coefficients are the Fourier coefficients. Right. So if you compare, our A0 will be 1, A2 will be minus 1 by 4, A minus 2 will be minus 1 by 4, and A3 will be 1 by 4, and A minus 3 will be 1 by 4, and any other AK are 0 for K not equals to 0, plus minus 2, plus minus 3, because we don't need those harmonics. Right. So this is, yeah, actually they asked us the Fourier series expansion of x of t, but we have also computed the Fourier coefficients. Right. So I hope this is clear, right? Can I move forward?
Yes, sir.
Okay, great. So now sometimes it's very hard to expand and see, look at the Fourier series coefficients. So we have a direct formula which we can use to compute the Fourier coefficients. Right. So, and I always recommend this is like in one time period. Okay. So either you integrate from 0 to t or minus 2 t by 2 to t by 2, it doesn't affect. So when I say integral and t here, all it implies that you have to integrate it over a period. Okay. So this is like this. And as I suggested, for computing this, for using this formula, you compute A0 separately and then A case when K not equals to 2. And this A0 is called average value over a period. Okay, so let's try to use those formulas and let's get a good grip on how to use this formula. Okay, so consider this square wave x of t, and you can clearly see, so it's a periodic, okay, it's a square wave, it is continuous. So x of t is 1 in the interval 0 to pi and minus 1 in the interval pi to 2 pi. Yeah, DC components means is A0, correct. So A0 is DC component. Okay, so now let's compute the Fourier series coefficients. Let's start with A0. Okay, so here you can clearly see in over the time period. So time period is 2 pi, right? So, right. So omega naught will be 1. Okay. So in the time, in this particular time period, half of the time the value is 1, half of the time the value is minus 1. And as A0 is the average value, so average between 1 and minus 1 should result in 0. And so let's cross verify whether that is becoming 0 or not using the formula. Okay, so I have to integrate from 0 to 2 pi x of t dt. Alright, so this is 1 by 2 pi. I'll have to integrate 0 to pi 1 dt plus pi to 2 pi 1 dt. Sorry, minus 1 dt. Correct. And this is like 1 by 2 pi. Integral of 1 is t. And if I substitute the limits, it will just be pi minus 0 plus this is integral of minus 1 is minus t. And when I substitute, it will just be minus 2 pi plus pi. Right. So this is pi and that is minus pi. Pi and minus pi will get cancelled out and it will just save. Right. So our average value is also 0. Even A0 is also 0. Okay. So this is A0. Let's compute AK. So ak is again 1 by 2 pi integral from 0 to 2 pi x of t e power into e power minus j omega naught. Omega naught is 1 k t. Right. So I didn't write omega naught because omega naught is 1 because the time period is 2 pi. So again, split this integral 0 to pi, and this is 1 e power minus j k t dt plus pi to 2 pi. This is minus 1 e power minus j k t dt. Right. So now I should know the integral of e power minus j k t, or in other words, I should know what is e power at. So e power at's integral will be e power at divided by a, which is minus jk. Right, and the limits are pi and 0 plus, even this is minus e power minus jkt divided by minus jk. And the limits are 2 pi and pi. Okay, and this minus and minus, you can cancel it out. And then we have this 1 by 2 pi outside. And this is e power minus j k pi. Right, I have to substitute pi in place of t minus e power minus jk 0 divided by minus jk. That is the first limit substitution. And then the second one, it will just be e power minus jk 2 pi divided by jk minus e power minus jk into pi divided by jk. Right, so that's the second. And now I can simplify this further. So I have e power minus jk pi divided by jk minus, here also it is minus e power minus jk pi jk. These two will get added to each other, and it will just become minus 2 times e power minus jk pi divided by jk. And then this is 1 by minus into minus, it will just be plus. So it will just be plus 1 by jk. Similarly, this one also, you see e power minus jk 2 pi. Right. So what will that be? Let me ask you this. E power minus jk 2 pi. What will this turn out to be? E power minus jk 2 pi is cos k 2 pi minus j sin k 2 pi. And k is an integer. What will this be? Oh no. I expected at least one of you will answer. Okay. What is sin k 2 pi? When k is, let's say, 10. What is sin 20 pi? 0. Okay, go back and see this. So this will be 0. This will be 1. So e power minus jk 2 pi is actually 1. Okay. So this will also be 1 by jk. So if I add 1 by jk with 1 by jk, this will be 2 jk. And 2, 2 you'll get cancel. And The result will be 1 minus e power minus jk pi divided by jk pi. Okay, so that will be the solution. Okay, even this also you can further simplify this if you want. So what will this be? E power minus jk pi. E power minus jk pi. This will be cos k pi minus j sin k pi. So again, what is sin k pi? Come on, you should know these values. I don't know why you guys are getting confused. But yeah, anyway, sin k pi is also 0. And cos k pi will oscillate between plus and minus. Right? So when k is even, it will be plus 1. When k is odd, it will be minus 1. Therefore, this will be 1 minus cos k pi divided by jk pi. Right? And you can also remove that cos k pi if you wish. So if k is even, k is odd. Okay, if k is even, cos k pi becomes 1. 1 minus 1 becomes 0. 0 by jk pi becomes 0. So you will not have any even terms, even Fourier coefficients. And when k is odd, cos k pi becomes minus 1. So 1 minus minus 1 becomes 2. It will just become 2 by jk pi. Right, so we got the Fourier coefficients. We have a0. A0 is 0 anyway. So if I write x of t, this will be k is equals to minus infinite to plus infinite 2 by jk pi into e power jkt, and here is only you have to pick when k is odd, and also k when it is mentioned that k is odd, k equals to 0 will also be vanished. So this is what our x of t is. Okay, so I can write that x of t like this. The square waves Fourier series expansion along with Fourier series coefficients is this. Hope this is clear. If you have any doubts, you can ask. Okay, if no doubt, then try this also. Okay, so we just asked to find a naught. Right, so a naught is again here one period is from minus pi to pi. So the time period will be 2 pi. So omega naught will be 1. So before you compute the Fourier series coefficients, you write down this time period as well as omega naught, fundamental frequency. So once we have that, this will be 1 by 2 pi integral minus pi to pi e power minus t dt. Right? So it's just average value over a period. And this is 1 by 2 pi e power minus t, we know e power minus t minus 1. And the limits are pi and minus pi. Okay, so this will be 1 by 2 pi e power minus pi divided by minus 1 minus e power minus of minus pi divided by minus 1. So if you simplify this, we'll get 1 by 2 pi into e power pi minus e power minus pi. That will be a naught. Yeah, so something like that. I think you got a sign reverse. Right? It will be e power 2 pi minus 1 divided by 2 pi e power pi. Okay, just cross check. I think you missed this minus 1 in the denominator. You would have taken plus 1. Okay, so if they ask you to compute A2, what will you do? So for AK we know the expression. A2 will be 1 by 2 pi integral minus pi to pi x of t is e power minus t into e power minus j, k is 2, omega naught is 1, t dt. That's it, no? So 1 by 2 pi minus pi to pi e power minus t into e power minus 2jt into dt. So you can club this e power minus of 1 plus 2j of t dt. And from here, I think you can solve. Right? You know e power 8 is expression, and from there I expect you guys to solve this. Okay. Yeah. Now this is really interesting, and I think you should all know this. This is impulse train, but not exactly the impulse train. It is scaled impulse train. As you can see, we have impulses once in every 2 units. Right? All we asked is to compute the Fourier series coefficients. Okay. Yeah, very good. So firstly, we should see what is the time period. So what is the time period? What is the time period of this signal? Good. 2. Right? So if time period is 2, omega naught is pi. Right? So these two things are clear. And we will take one time period is sufficient. Right? So all we need is one time period. We will pick minus 1 to 1. Okay. So if you pick minus 1 to 1, I'll have to compute A naught, right? So A naught is 1 by 2 integral minus 1 to 1, and we have x of t as delta of t dt. And what is the integral of minus 1 to 1 delta t dt? What is area under the Dirac delta? Yeah. All right. So this we have seen extensively in week 4, no? So when you integrate the Dirac delta, when the impulse is within the limits, that will integrate to 1. And this will be half into 1, which is half. All right. Nice. A naught is half. What about AK? Other coefficients AK. So this will also be half integral from minus 1 to 1 x of t e power minus j k omega naught is pi t dt. And we know x of t is delta of t e power minus j k pi t dt. All right, so now let's test your understanding of Dirac delta. So what will happen when I integrate inside the integral? If I have delta of t and some signal, some other signal x of t is getting multiplied, what will this be? So if this is some y of t. Okay, so what is integral delta t y of t dt? Okay, so Nanda says it's 1. What will this be? Tell me in terms of y. Yeah, at t is equals to 0, it samples, and this will be y of 0. If you remember correctly, we defined actual way of defining Dirac delta. Yeah, you should recall all these things. So when I integrate the signal multiplied with, yeah, that should be minus infinite to plus infinite, but you don't need minus infinite to plus infinite. No, when our impulse is at t is equals to 0, all you need is some minus epsilon to epsilon. Yeah, so delta should be within the limits. That's it. Okay, so this will be y of 0. Here y of t is e power minus j k pi t, and y of 0 will be e power 0, which is 1. So that will be half into e power minus j k pi into 0. So this will give us ak to be half. Right, so a naught is half, ak's are also half, and this is half for all k. Right, so therefore I can write the Fourier series expansion as Fourier series expansion x of t as summation k is equals to minus infinite to plus infinite half e power j k omega naught is pi t. Right, so this is the Fourier series expansion of the scaled impulse train. Okay, so we didn't take the impulse train exactly. We have scaled it. Like see, we have expanded it. Right, so even the Fourier series coefficients are just the scaling factors of the expansion. Okay, I hope this is clear. And what I want you guys to try it out is, okay, here I scaled it by half. What if I scale it by, what did I do? What if I scale it by, or what will be the Fourier series coefficients of this signal? T, 2t, 3t, minus t, minus 2t, 0. No, not 1 by 3. It's 1 by t. Okay, so firstly, you should understand that this signal has a time period of capital T. Right, so it's a generalized version of the impulse train. Okay, maybe try it out. If you have any answers, you can start the discourse thread or in the G space. Okay, let's put it as an exercise. Okay, so moving on, we have many Fourier series properties. Yeah, In lecture, sir has also discussed it. Go back and watch it again. And yeah, so these properties will help us to compute the Fourier series coefficients of some other complicated signals. Okay, so that is why we use these properties, and I'll just wrap this up very quick. So the linearity property states that if I have a signal x1 of t, right, and its Fourier series coefficients are ak, x2 of t has bk, then alpha times x1 of t plus beta times x2 of t signal will have Fourier series coefficients as alpha ak plus beta bk. And if I just shift the signal, then the Fourier series coefficients will get multiplied by some scaling, some value, which is e power minus jk omega naught t naught. Okay, so that is time shifting. Time scaling, yeah, as discussed in the lectures, that is also one way. But usually in most of the textbooks, it follows this thing. So scaling will not affect the Fourier series coefficients. Yeah, so a k by c is, when k by c is not an integer, no? So it results as some other different things. So that is also a possibility, but most of the textbooks follow this thing. Time scaling usually will not affect the Fourier series coefficients, rather it will affect the frequency. Okay, so the omega naught will update to, or sorry, the frequency will become omega naught into c. Okay, so it will not come into the coefficient, it will go into the phase part. Okay, so that is time scaling, and with that you can solve these problems. So x of t with time period t and ak's are the Fourier series coefficients. Then x of t minus 2 will have Fourier series coefficients as ak into e power. Right, so this is shifting. If you are delaying, you will have minus. So this will be e power minus jk. Time period is capital T, so omega naught will be 2 pi by capital T into 2. The T naught is. And this is the Fourier series coefficient for x of t minus 2. And for this, the Fourier series coefficient will be ak e power minus jk, sorry, plus jk 2 pi t, and the delay is 3. Right, and there is a linear combination between these two signals. Therefore, the Fourier series coefficient bk will be ak into this plus 2 times ak into this. Then you can pull out ak out, and this will be e power minus 4 jk pi by capital T plus 2 times e power j 6 jk pi by capital T. So this will be the Fourier series coefficients. Okay, and x of 10t, just now we explained, no? Just now we said this will have the same Fourier series coefficient ak, but the only change will be omega for this will be it is not just 2 pi by capital T, it will just be 10 into 2 pi by capital T. So that will be the frequency. Okay, that is 20 pi by T. Alright, so that is there. So this is the example. I wrote 5. And this is the fourth property, which is really important, which is called Parseval's theorem. And the idea of Parseval's theorem is energy is getting preserved. Right, so you whichever way you represent, finally if I compute energy, I should get the same value. So you represent the signal in Fourier series representation, or you take the signal as it is. The signal is the same. And if I compute the energy, I should get the same energy in both ways. Right. So that's the idea of Parseval's theorem. Energy is preserved. Right. On the left hand side, you take the signal as it is and you compute the energy of the signal. Since these are periodic signals, this we will just work with average power. Right. So so let me put the statements very carefully. Okay. So this is energy over a time period, which is also power. Right. So if total energy is preserved, even in one period, energy should be equal. So this is average energy. So it's an average energy over a period on the left hand side. And on the right hand side, if you compute the power, this average energy is nothing but the power. And the right hand side is also the power through Fourier series coefficients. So you compute that e power j omega t. If you take the absolute value, that will just become 1. And you will just have absolute values of ak whole squares when you compute power. Okay, so that way, the left hand side and the right hand side should be equal. Because that is what Parseval's theorem states. All right, I hope this is okay. And let's solve a problem. Solve the same problem. Above I gave it graphically. Below I'm giving it like this. Okay, so this is x of t for us. And if I compute, I have to compute the power. It is average energy over a period, which is 1 by 2 minus 1 to 1. X of t in that interval is delta of t whole square dt. And as we know, delta t whole square is not computable, right? So we can't compute this. But we can use this Parseval's theorem. And we know that this is actually equals to summation k is equals to minus infinite to plus infinite ak's whole square. Right? And we know this signal's coefficients, Fourier series coefficients, just now we have computed, it will be half for all k, no? So when I substitute it, power will just become summation k is equals to minus infinite to plus infinite half whole square, which is 1 by 4. And you are adding 1 by 4 infinity times. You will see that this is infinite. So when we try to compute power of an impulse train signal, even the power will also be infinite. Right? So that is about the Parseval's. And yeah, there is one more problem which actually uses this Parseval's theorem. Okay, so whenever coefficients are given to you and they're asking for power, it means that you have to use the Parseval's theorem. Okay, so here is an example. X of t is a periodic signal with capital T and has Fourier series coefficients ak given as follows. Okay, so when k is greater than or equals to 0, ak's are 1 by 2 power k when k is even and 0 when k is odd. When k less than 0, ak's are 3 power k when k is odd and 0 when k is even. Within a fundamental time period, it is 1 by 4. Yeah, but we have to compute the whole signal's power, no? Yeah. Signal is not just delta of t, right? So signal is this. Right? So did I write? Just a second. Even I'm getting confused here. Did I write the correct expression for Parseval's theorem? This is what Parseval's theorem, no? Can somebody confirm? Oh my God. Yeah, right. So, all right. So that's the Parseval's theorem. And again, if they ask you to compute the power, it is yeah. So if they ask you to compute the power and they are giving you the Fourier series coefficients, it is evident that you have to use this Parseval's theorem. Okay. So here also you can see we have given the Fourier series coefficient, but in a different manner. But all we can do is the power will always be summation k is equals to minus infinite to plus infinite absolute value of ak whole square. That will be the power. So here it is given k less than 0, k greater than 0 in different fashions. But you can separate it out. You can take like minus infinite to 0 or 0 is included above, minus infinite to minus 1 mod ak whole square plus 0 k is equals to 0 to infinite mod ak square. Right. So this will be only the odd terms will be there. So k is equals to minus 1, minus 3, minus 5 and so on. So this will be a minus 1 whole square plus a minus 3 whole square plus and so on till minus infinite it goes plus here a0 square plus a2 square. Only the even terms are there. Only the even terms will be there. Okay, so we know a minus 1 is 1 by 3. So it is 3 power k, no? So 3 power minus 1 is 1 by 3 whole square plus 1 by 3 cube. Right, so when k is minus 3, it is 1 by 3 cube, 1 by 3 cube whole square and so on. Plus a0 is 1 by 2 power 0, which is 1 square plus a when k is 2, 1 by 2 power 2 is 1 by 4 and whole square. So don't forget that whole square. Okay. And this is a geometric series. This is a geometric series. You can compute. You can see this is the starting term is 1 by 9. A is 1 by 9 and the ratio is the next term is 3 power 6. So the common ratio will be 3 power 4. So 1 by 3 square and 1 by 3 power 6. So there is a difference of 1 by 3 power 4. And here also A is 1 and the common ratio is 1 by 2 power 4. Okay, so use the formulas of geometric progression, geometric series and substitute them, you'll get the answer. Okay. All right. So this substitution and these things, I hope you can do. Right. So these are the important concepts that you should focus and prepare well. And we will on Saturday we will do more problems again. and the problems will be the mock problems. Okay, so the mock test, we have released it. Try to solve them, and on Saturday we will do that mock. Along with, if at all, if you have any other questions also, you can ask in that Saturday session. All right. So with that, we will end our session here. We have discussed a lot of things. Take a break. Maybe not. Maybe don't just come back today. Take a break today. Either tomorrow morning or we all are exhausted. I agree to that. Okay, so even if I am a student, even it's very hard for me to sit for 2 hours and listen to many different concepts. So that is why take a break tomorrow morning or tomorrow afternoon. Just come back and see what all we discussed and solve problems related and around these concepts more. Okay. All right, guys. We will meet maybe on Saturday. If not, maybe after the exam. All the very best for your exam. Quiz 1, most of us didn't do well, but I hope quiz 2 will be good for all of us. Okay, so on Monday we should meet with happy faces. All right, guys. Thanks all for joining and have a great day.